Welcome back to Engineering Out Loud. We're on the 5th episode of our series from MECHESOL's MESP Engineering Development Program, and today we're going to be diving deep into the world of simulation and analysis.
Awesome.
And if you are digging what you're hearing, don't forget to check out the program and apply at mechesolco.com/CPD.
Okay, so let's talk simulation.
Okay.
Imagine testing product designs and seeing how they perform under different conditions, all without actually building anything physical. That's the magic of simulation tools.
Okay, I'm intrigued, but what exactly is simulation?
Right.
And how does it actually work?
So simulation is all about creating a virtual model of a system or product, kind of like a digital twin.
Okay.
We use computer algorithms to analyze its behavior under various conditions. It's like having a virtual laboratory.
Wow, virtual lab.
Right on your computer.
It sounds incredibly powerful.
It is.
So what are the real-world advantages of using simulation in engineering? Like, why should engineers care about this?
It's a game changer, honestly.
Okay.
First off, remember those expensive physical prototypes engineers used to build?
Yeah.
Simulation drastically reduces the need for those. That means faster development cycles and significant cost savings.
Makes a lot of sense. Faster and cheaper is always a good thing.
Always. What else can simulation do?
It also allows you to test designs in extreme conditions.
Oh, wow.
That would be really difficult or even dangerous to replicate physically.
Okay.
Think simulating a hurricane's impact on a skyscraper or a rocket launch into space.
Oh, wow.
You can analyze the effects of different materials, loads, and environmental factors on your design, gaining insights that would be really tough to get from physical testing alone.
So simulation helps you design things better, faster, and cheaper.
You got it.
But I'm guessing there are different types of simulations, right?
For sure.
Not everything is a rocket launch.
Right.
Or a hurricane.
Right.
There are various types of simulations, each tailored to a specific need.
Okay.
Like if you want to know how strong a bridge is, you'd use a structural simulation. To study how heat flows through an engine, you'd use a thermal simulation.
Makes sense.
And to understand how air flows around an airplane, you'd use a fluid dynamics simulation.
Okay.
There are even simulations for analyzing electrical circuits and how they behave.
So it sounds like simulation has a tool for every engineering challenge.
Yeah.
Okay, so let's say you want to run a simulation.
Right.
What does that process actually look like?
Think of it as like a journey with a few key steps.
Okay.
First, you define the problem you're trying to solve.
Okay.
What are you trying to learn?
Right.
Once you've got that figured out, you build your simulation model.
Right.
This is where you create the digital twin, defining the geometry, materials, and other details of your design.
So you're essentially building a digital replica of your product.
Exactly. Then you apply boundary conditions, which mimic real-world scenarios.
Got it.
This could include things like forces, pressures, temperatures, or even the surrounding environment.
Okay.
It's all about setting the stage for your simulation.
So like adding wind resistance to your airplane design.
Right. Once the stage is set, it's time for the computer to do its magic.
Okay.
This is the analysis stage, where the software uses powerful algorithms to solve complex mathematical equations based on your model and boundary conditions.
So it's crunching all those numbers to predict how the design will perform, right?
Yep.
Okay.
And finally, you interpret the results.
Okay.
This means analyzing the data graphs and visualizations generated by the simulation to see how the product behaves. Remember, the goal is to use those insights to improve your design.
It's not just about running the simulation, it's about understanding what the results tell you, right?
Exactly.
Okay.
This entire process is also iterative. You often refine the model and rerun simulations based on those initial results, gradually improving the design until it meets the performance goals.
So it sounds like simulation really empowers engineers to make data-driven design decisions.
Absolutely.
Awesome.
And for those of you interested in taking a deeper dive into simulation,
Yeah.
MECHESOL's MESP Engineering Development Program is a fantastic resource.
Don't forget, you can learn more and register at mechesolco.com/CPD.
Right.
Now, I know you mentioned earlier that there are different types of analyses used in simulation.
Yeah.
Can you break those down a bit further for us?
You got it.
Okay.
Let's start with one of the most common types, structural analysis.
Okay.
This focuses on how a structure responds to loads and forces, like weight or pressure.
Okay.
You're analyzing things like stress, strain, deformation, and even the potential for buckling or bending.
So with structural analysis, you can figure out if a bridge is strong enough to support traffic, right?
Exactly. Another important type is dynamic and vibrational analysis.
Okay.
This type investigates how a structure reacts to dynamic loads and vibrations, which is crucial for anything that moves or shakes.
Right.
Cars, airplanes, machines, you name it.
Got it.
So it's all about understanding how things move and vibrate in the real world.
That makes sense. What other types of analyses are there?
Well, there's thermal analysis,
Okay.
which is all about heat flow.
Okay.
It helps you predict temperature distribution, heat transfer rates, thermal stresses, and even things like thermal expansion.
Okay.
It's essential for designing electronics engines and anything that generates or experiences heat.
Okay, so thermal analysis helps you make sure your phone doesn't overheat in your pocket.
Exactly.
Got it. What about things that involve liquids and gases?
Yeah.
Is there a specific type of analysis for that?
You bet. It's called flow analysis or computational fluid dynamics.
Okay.
CFD.
CFD, got it.
It simulates the behavior of fluids, both liquids and gases. CFD helps us understand everything from the aerodynamics of an airplane to how water flows through pipes.
Wow, that's a lot of different analysis types.
Yeah.
It seems like there's a tool for every aspect of engineering.
It really does.
But how do engineers actually create this virtual environment for their simulations?
Yeah.
What are the steps involved?
Creating a virtual environment is a multi-step process that takes careful planning.
Okay.
First, you need to determine which type of analysis you'll be performing.
Okay.
This is important because it influences every step that follows.
So choosing the right analysis type is like setting the foundation for the entire simulation.
Exactly. Once you've got that figured out,
Yeah.
you move on to creating the geometry.
Okay.
This means either building a new 3D model within the simulation software or importing an existing one from a CAD program.
Okay, so you're basically creating the digital blueprint of the product you want to analyze.
Precisely, this digital representation needs to be accurate and detailed to ensure your simulation results are reliable. Next comes defining the material properties of your model.
Material properties, what does that mean exactly?
Think about it. Every material behaves differently under different conditions.
Sure.
Steel reacts differently to stress than plastic, right?
Right.
So you need to tell the simulation software things like the density, elasticity, and thermal conductivity of the materials you're using.
So these properties tell the simulation how the material will respond to heat force and other factors. It's got to be accurate or your results won't be either.
Right on, after you've defined your materials, you move on to mesh generation.
Mesh generation, what's that all about?
Imagine you have a complex 3D model.
Okay.
To run calculations, the computer needs to break down this geometry into smaller, more manageable pieces. That's what mesh generation does.
Okay.
It divides the model into a network of small elements, creating a computational mesh.
So it's kind of like taking a big puzzle and breaking it down into individual pieces that the computer can understand.
That's a great way to put it. The smaller the elements in the mesh,
the
more accurate the simulation will be. But it also requires more computational power.
I see. So it's a balancing act between accuracy and computational resources.
Exactly. Now, once you have your geometry materials and mesh sorted out, it's time to apply boundary conditions.
You mentioned boundary conditions earlier. Those are all about mimicking real-world scenarios, right?
You got it.
Okay.
It's like setting the stage for your virtual experiment. You need to tell the software how the model will interact with its environment.
Right.
For example, if you're simulating a bridge, you'd apply forces to represent the weight of traffic, wind loads, and maybe even seismic activity.
It sounds like boundary conditions are crucial for making sure your simulation reflects real-world conditions. What happens once all of this is set up?
That's when the computer takes over in the solution or processing stage.
Okay.
The software uses powerful algorithms to solve all those complex mathematical equations we talked about earlier.
So it's crunching all the numbers based on the model, materials, and boundary conditions you've defined.
Exactly, depending on the complexity. This stage can take anywhere from minutes to hours or even days to complete.
Wow.
But once it's done, you move on to the most important step of all.
Which is?
Results interpretation.
Okay.
This is where you make sense of all the data generated by the simulation and extract meaningful insights that you can use to improve your design.
It sounds like results interpretation is all about turning raw data into actionable knowledge.
You nailed it. You analyze the data graphs and visualizations to understand how the product behaves under the conditions you've set.
Yeah.
How much stress is it experiencing?
Right.
How does heat flow through it?
Right.
Is it aerodynamically efficient?
Yeah.
These are the kinds of questions you're looking to answer.
Wow. It's like being a detective, but instead of solving crimes, you're solving design challenges.
Exactly.
So what happens next?
Well, based on your interpretation of the results, you can then identify areas for improvement. Tweak your design,
right,
and run the simulation again to see how the changes affect performance.
Okay.
It's an iterative process, constantly refining and optimizing the design until you achieve your goals.
This whole process, from setting up the virtual environment to interpreting the results, really highlights the power of simulation in engineering.
It absolutely does. Simulation allows engineers to move beyond guesswork,
Right.
make data-driven decisions, and create innovative products with confidence.
Awesome.
And for those eager to delve deeper into this exciting world, don't forget to check out MECHESOL's MESP Engineering Development Program. You can apply right now at mechesolco.com/CPD.
Thanks for the reminder. So now that we understand the steps involved in running a simulation, let's shift gears and talk about a really cool application, virtual prototyping.
Yes, virtual prototyping.
Yeah.
Remember how we talked about simulation reducing the need for physical prototypes?
Yes.
Well, virtual prototyping takes that concept to a whole new level.
It's like having a digital playground where you can test out all your ideas without any real-world consequences.
That's a great way to describe it. Virtual prototyping allows you to create and test a fully functional digital twin of your product entirely within the virtual world.
So instead of building a physical prototype, you can build, test, and refine your design digitally.
Exactly. Virtual prototyping leverages the power of simulation to give you a realistic and interactive representation of your product's behavior.
Right.
Long before you manufacture any physical parts, it's a game changer for product development, especially for startups or companies with limited budgets.
I can see why, but what are some of the specific advantages of using virtual prototyping?
Well, first off, it drastically accelerates the design process.
Okay.
Think about it. If you want to make a change to a physical prototype, you have to physically modify it, which takes time and resources. With a virtual prototype, you can just tweak the digital model and rerun the simulation.
So it's like having a fast-forward button for the design process.
Precisely. And of course, it significantly reduces prototyping costs.
Makes sense.
Building physical prototypes can be incredibly expensive.
Yeah.
Especially for complex products, virtual prototyping lets you avoid those costs and allocate your budget more efficiently.
That's a huge advantage.
Yeah.
What other benefits does virtual prototyping offer?
Well, it also enhances your design efficiency by providing a virtual platform for testing and experimentation. Virtual prototyping allows you to identify and address design flaws early in the process before they become expensive problems in the real world.
It's like catching errors before they have a chance to multiply. So virtual prototyping helps you create better products faster and cheaper.
Exactly. It's all about using data and simulation to make smarter design decisions. And one of the key aspects that makes it so powerful is its integration with CAD software. The tools used to create those 3D models we talked about earlier.
So you can design your product in CAD and then seamlessly import that model into the virtual prototyping environment.
You got it. This streamlined workflow eliminates the need for data conversion or manual model recreation, saving you time and reducing the risk of errors.
It sounds like virtual prototyping is all about making the design process as smooth and efficient as possible.
Absolutely. And once you have your virtual prototype set up, you can run those simulations we talked about earlier and gather a ton of data about the product's behavior, stress distribution, heat flow aerodynamics, and more.
So you're moving from guesswork to a data-driven design process.
Exactly. And remember, this entire process is iterative. You can make changes to your virtual prototype based on the simulation results, run the simulations again, and keep refining your design until you achieve the desired outcome.
It's like having a virtual laboratory where you can experiment and test different design options with incredible accuracy.
That's a great analogy. Virtual prototyping is a game changer in the world of product development, and simulation is at the heart of it all.
This whole deep dive into simulation and virtual prototyping has been fascinating. It's amazing how much engineering has advanced thanks to these powerful tools.
I agree, and if you're ready to explore these tools further, I encourage you to check out MECHESOL's MESP Engineering Development Program at mechesolco.com/CPD.
Yeah, it really does put the power to shape the future right in our hands.
It absolutely does. And hey, if you're ready to start shaping that future, don't forget what we talked about earlier.
Right.
MECHESOL's MESP Engineering Development Program is the perfect place to dive in. Head over to mechesolco.com/CPD to apply.
That's right. You'll get hands-on experience with the latest simulation tools and techniques.
Yeah.
Plus, you'll be learning from some of the best in the industry.
Absolutely.
It's an amazing opportunity for anyone who's serious about a career in engineering.
For sure.
Well, this has been another incredible deep dive.
Yeah, it has.
Thanks for joining us.
My pleasure.
And thanks to you, too, for sharing all of your insights with us.
It was my pleasure.
Until next time,
Yeah.
keep engineering out loud.
Keep engineering out loud.